force we're going to talk about in more detail today is the spring force, also called the elastic force. And there's an equation that tells us how strong this force is, what its magnitude is. And that equation was designed or discovered by a physicist named Robert Hooke. And the equation is commonly known as Hooke's law, hence the title of this lesson. So the idea here, as you guys probably are aware if you've ever played with a spring or an elastic band, is that a lot of objects, when you misshape them, either you stretch them out or you squish them together, they push or they pull back on you, and they want to get back to their original shape. That's the general idea behind the spring force or the elastic force, is that this is the force with which a distorted object tries to get back to its original, or in other words, its equilibrium state. And just so you know, spring force and elastic force aren't like two different versions of this force. These are just two names that it has, and they're used interchangeably. I usually call it the spring force, but sometimes you'll hear it called the elastic force as well. Now, I want to start this lesson off by saying that this is a more important force to study than you would think. A lot of things that engineers build or design don't really have bouncy stuff in them. Springs and elastics aren't used, everywhere. So in Physics 11, where we're studying really common forces like gravity, like friction, like normal force, these are everywhere. It might seem a little weird that we're suddenly getting kind of niche and looking at springs and elastics. But the reason why this force is so important is because literally every object is a spring and is an elastic, even though they don't seem like that at first. And to demonstrate this, I want to show you sort of a quick clip here. This is a golf ball, and this golf ball has been fired at a steel plate. And watch what happens. So the reaction most people have to this video is sort of surprise. You think of golf balls as being really, really hard, really tough to bend. But you see in this video, this golf ball behaves almost like it's a liquid. It really distorts very, very easily in a number of different ways. And that's kind of what I'm trying to get at here, is that every object is bouncy like this. Every object behaves like a spring. A big rock, if you grab it and put your hands on both sides and squish, it actually does shrink. It gets a bit smaller. And like a spring, it pushes back on you, trying to get back to its same shape. Now, a rock doesn't compress nearly as much as the average spring does, because or provided you don't put too much force on it. When structural engineers design buildings, big, tall buildings, they actually treat every steel beam and every piece of concrete in that building as if it's a spring, and they calculate how much the concrete is going to compress by, how much that steel beam is going to expand by when these forces are put on it. So that's why this topic of the spring force is a lot more important to physics and to engineering than it might seem at first, because we use it all the time for a variety of objects that you wouldn't normally think of as behaving like springs. Now, this particular video that I just showed you here with the golf ball, there's if you do decide to watch that video yourself, there's some discussion down here in the comments about how legitimate that video is. There's discussion on both sides. My personal take is that this is a very extreme situation. You don't normally see golf balls deform this much, but I think it's probably possible under really, really specific conditions, and it's possible that they set those up in this video. But there are lots of other videos you can see of golf balls getting hit by clubs and deforming and bouncing, although not quite as much as this video shows. Okay, so hopefully I've instilled in you that the elastic force is an important force to study because everything behaves like a spring, like an elastic. Let's look into how we can calculate this force. So Hooke's law is this equation right here. It says the spring force, or the magnitude of the spring force, is equal to K times X. So let's unpack this. Fs, as I said, is called the spring force, also called the elastic force. K is called the spring constant, and you'll also hear it called the stiffness. So this depends on the material. Something like a rock is going to have a very large value of K. It's going to be very, very stiff. Something like a little elastic band that you maybe play with when you're a child is going to have a very low value of K. It's not going to be very stiff. It's very easy to bend. So you can think of this as how hard it is to deform or bend something. And X represents the change in length of the thing that you're trying to deform. And this is also sometimes called the displacement. How much you've moved that thing from its original shape. Okay, so units are going to be important here too. Well, the spring force, like every single force ever, is going to be measured in newtons. And X is the change in length. Well, it would make sense we'd measure that in metric base units for length, which are meters. And that means that K, the spring constant, we could actually figure out its units if we just do a little math here. So if I want to isolate K, I would bring X to the other side of this equation, and I'd end up with Fs divided by X. So to find the units of K, I would take the units of Fs and divide them by the units of X. So I end up with newtons divided by meters, or newtons per meter. And that is exactly what the units of K are, newtons per meter. And that actually tells us a bit about K. If a material has a stiffness of 3 newtons per meter, that means for every meter you stretch it with, it's going to pull back with 3 newtons. So if you pull it 2 meters, it's going to pull back with 6 newtons. If you stretch it 6 meters, it's going to pull back with 18 newtons. This is the number of newtons it's going to pull back or push back with when you deform it for every meter its length changes by. One thing I want to note about this equation, which I haven't actually brought to light, although it's been happening for a while now, is there are no vector hats in this equation. And I want to explain to you sort of why that is. If you have a look at your formula sheet, a lot of the formulas that we've been going over in this course, you'll see that there are some with vector hats and some that aren't. For example, down here in the forces unit, I've told you guys that force is a vector. Force has magnitude and direction. And here in Newton's second law, force has a vector hat. But down here, all these force equations do not have vector hats. Now, that doesn't mean that the gravitational force is not a vector or that the frictional force is not a vector. They are. But the reason I haven't drawn the vector hats here is because this equation will not tell us the whole vector. This equation can tell us the magnitude of gravitational force. But we have to go and figure out the direction on our own. This equation will tell us the magnitude of a friction force. But we have to go and figure out the direction on our own. This equation will actually tell us the magnitude and the direction of the net force. So this equation will actually give us the entire vector, so I've included the vector hats here. These other equations, these are still vectors, but the equation doesn't tell us the whole story. It just tells us the magnitude. So whenever in an equation you see a symbol that usually represents a vector, but there's no vector hat on it, that just means the equation doesn't tell you the whole story. It just tells you the magnitude. Okay, so this equation will tell us the magnitude of the spring force. All right, so let's try an example with this. A student stretches an elastic cord with a stiffness of 50 newtons per meter by 15 centimeters. How much force is the student applying? So you can imagine here, students found an elastic cord, a little bungee cord somewhere in a classroom. One end of the cord maybe is attached to a wall or a desk, and they're pulling on the other end. And they are managing to stretch it by 15 centimeters. So the cord is now 15 centimeters longer than it normally would be. We want to know how much force must the student be applying to make this happen. Okay, well, let's start with our new equation. Spring force equals K times X. If I put some numbers in here, K is going to be the stiffness, or the spring constant, which is 50 newtons per meter. That's metric base units, so that's great. It can go straight in. X is going to be the change in length, so how much the student stretched it by. And we know that's 15 centimeters. This isn't metric base units, so I'm going to have to convert that to meters. That's going to become 0.15. So my K is 50, my X is 0.15, and I find that the spring force in this scenario is 7.5 newtons. Now, remember, the spring force is the force with which a distorted object tries to get back to its equilibrium state. So this is how hard that cord is trying to get back to its original length. This is how hard the cord is pulling on the student, the force that the cord exerts on the student. Now we were asked how much force is the student applying to the cord. Quickly thinking about Newton's third law here will be helpful. Newton's third law says every action has an equal and opposite reaction. So if the cord is exerting 7.5 newtons on the student, that means the student must also be applying 7.5 newtons to the cord. So the answer to our question, how much force is the student applying, is that the student applies to the cord a force of 7.5 newtons, but in the other direction. So if the cord's pulling the student to the left, the student's pulling the cord to the right. All right. Next example is going to be a little bit more involved. And this example, I actually was inspired for this example by a video I once saw. And the video is over here. It's this video right here. I won't actually show the whole thing to you right now, but if you want, you can go to YouTube. You can have a search for it, and it should come up. You can watch the video. I would suggest watching it to just before the release, then come back here. We'll solve the problem together, and then you can go watch the rest of the video at the end. So, in this video, I kind of watched it, and I took my best guess at a few of the numbers in it. There's a girl. I'm guessing she's about 65 kilograms, and she sits in what the video has referred to as a redneck slingshot. She's got a couple of elastics attached to her. A common spring constant for, general consumer bungee cord material is about 31 newtons per meter. And I'm guessing from when I watched the video that they stretched that sling back by about 22 meters before they released her. What is her initial acceleration? How many G's is that? Will she survive, and did we make any assumptions? Okay, so as with any forces problem, we're going to start by setting up a free body diagram. So here's my girl sitting back in her slingshot, and she's got a couple of forces acting on her. There's a spring force from one of the cords, and there's a spring force for another one of the cords. Just to give you an idea sort of what this situation looks like, here's another example of a similar slingshot that I dug up. So we've got a couple of upright posts, one here and one just off the screen. Some elastic cords coming back to this person who's in a harness, and then they're usually towed back by some kind of machine and then released. So these are the two spring forces from those two elastics that are tied to them. Now also, there would be maybe a force from that machine they were attached to holding them back this way. Maybe they'd have their feet dug into the ground with some friction, stopping themselves from flying off. But what we're interested in is the initial acceleration, meaning the moment that she is released, what's her acceleration then? And when she's released, that instant, it's either because this machine that was towing her back has let go of her, so that force is gone, or it's because maybe she's lifted her feet off the ground to release herself, so that friction force is gone. So we've just got When she's released, we've just got these two spring forces on her left and on her right. Once I've done a free body diagram, good practice is to quickly find any forces that are going to be easy to find. And we now know spring force is pretty easy to find. Using spring force equals K times X. Here, K is 31, X is 22 meters. So the spring force is 682 newtons. So both of these, she has, remember, two elastics tied to her, one to each side, and they're both going to be 682 newtons. Okay, so there's our good free body diagram. We've got some good information there. What is her initial acceleration? So far, all we've really got information on here is forces. But acceleration, that's more of a motion, a kinematics concept. What's the big important equation we have that links the world of forces with the world of motion and kinematics? That is Newton's second law, or F equals ma. Okay, so here I'm going to add up all the forces that are acting on her, sum them together. That's going to be equal to her mass multiplied by her acceleration. So she's got two of these, a 682 in the positive direction and another 682 in the positive direction. There they are. Her mass is 65. There's her acceleration. We quickly solve this. We find that her acceleration is 21 meters per second squared in the positive direction. And here I'm calling that forward. I think in the video, if you watch it, she's actually going, to the left across the screen. So we're just saying forward. Okay, so we've solved the first part. What is her initial acceleration? Next thing you might be asking is, how fun is this ride going to be? 21 meters per second squared. Seems like kind of a big acceleration. What's that going to feel like? Well, let's figure out how many G's she's experiencing. What's the G-force that this ride imparts? So G-force calculations. I'll remind you here, because it's been maybe a few days since you've done G-force, that what G-force does is it compares the contact forces to the object's weight. So remember, there are some forces that we call body forces. Gravity is an example because gravity acts on the whole body. Gravity, would act on your head, it would act on your shoulders, it would act on your hands, your arms, your knees, your legs, your feet. But other forces are called contact forces. They only act where objects are in contact. And this is an example of one of those. This spring force here is not pulling on her head or her legs. This spring force is just pulling on her body where the elastic is in contact. So we want to look at all these contact forces and we want to compare them to the object's weight. And that tells us the G-force, sort of the weight that this person is experiencing. So first of all, her weight is going to be 637 newtons. That needs to be just quickly calculated. Then we compare these contact forces to that. So if I add these two together, I get maybe 1,300 and something newtons. And I find out that that combined number is about 2.1 times her weight. This net force here from all these contact forces is about 2.1 times her weight. So she feels about 2.1 Gs. Now, you might recall that I said the average person can feel or can withstand about 4 Gs before they have to worry about blacking out. So this is going to be a fun ride for her. 2 Gs is noticeable. You feel that, but she's likely going to survive. And in fact, that 4 Gs number I told you guys before, that's 4 Gs upwards that the average person can take. 4 Gs kind of sideways like this is much easier, and the average person can take quite a bit more than 4 Gs if it's sideways. So she's gonna be good. Maybe you know that already if you watch the video. Now, the last thing to talk about here is, did we make any assumptions? And yeah, maybe you caught this along the way. There are a few assumptions here that we made. One is, I didn't draw FG in the diagram here. Clearly she's on the planet Earth. She's going to have some weight. We even calculated it over here. We didn't draw it on the free body diagram. Also, I drew these spring forces as being totally horizontal. But in reality, in this photo and in the video, you can see they're kind of going up at an angle. So clearly what we've done here is not a super accurate representation of this problem. The reason I left gravity out and I didn't draw these at an angle is because I wanted to keep this problem one-dimensional. Everything moving along a straight line, in this case left, right. Gravity going down would have messed that up, and these guys going up at an angle would have messed that up. So if we want to do a more accurate analysis of this situation, we'd probably have to do some 2D forces solving. But for now, I just wanted to kind of keep it really simple and use this as kind of an introductory problem to get you thinking about spring force and remind you of this G-force stuff. Another way to think about this G-force in the horizontal scenario here is, so saying she feels 2.1 Gs means that these contact forces she's feeling are 2.1 times as big as her weight. It also means that her acceleration is 2.1 times as big as the acceleration of little g, as 9.8. If you take 9.8 and you multiply it by 2.1, that gives you this. That's her acceleration. So she's accelerating a little more than twice as fast as she would if she was just dropped and allowed to free fall at 9.8.